All right. So we looked at solubility. The solubility product seemed pretty easy. Well, that's usually the case, but we also have common ion effect. When one of the ions is already present, it's going to make a difference, makes it more complicated. So in general, you have stuff dissolve in water. No biggie. If there's more X or Y already there, then Le Chatelier's would say increasing the concentration of any product would shift it towards the reactants and therefore make more of the solid. So that means if there's already one of these present, the solubility of this is going to decrease because it's going to make more of these ions form more product, which means less is going to be able to dissolve. So let's go back to the one we had before, our calcium ions, our calcium phosphate solution. Let's say there's already some calcium chloride, and we're trying to see how much calcium phosphate will dissolve. Well, initially, we have some calcium, no phosphate. We add our ratios, so now we have our total amounts. So compared to 0.2 molar, S is going to be super small and therefore insignificant because the KSP value of this is going to be super tiny. Now we can't get rid of it when we have this, but we're talking about when we have these added together. So that means we can plug in our values, solve for S, get our S there, and our molar solubility is going to be far, far smaller than it was before. Okay? Much less soluble than when the ions are present. So keep that in mind that because these are already dissolving to a small amount, quite often we can eliminate the S if our concentration is very high. If this was much smaller, we would need to take that into comparison and significance involving that. So calculate molar solubility already containing so much calcium already. So we've got our ratios here. My initial 0.25, going to be 1s and then 2s. You can see I thought I was using x's. I have my two values here. S is going to be real small. Look at how small my KSP is. Okay, so my molar solubility is already going to be something to like the fifth, negative fifth. Way too tiny for this to occur. So I can eliminate the S here. I got my 0.25 times my 2S, solve for S. And so it's 2.92 times 10 to the negative 10th rather than the 3.32 times 10 to the negative 4th. I just looked this value up to see what was the comparison. So again, it's always going to go down. We can often eliminate S because the KSP is very small. Look at the molarity here, right? If that's just plugged in here, if I just added 3.32 times 10 to the negative 4th, that's not even going to show up for sig figs. That's like way over here. So I can often eliminate that value. Let's say we've got another one, very sparingly soluble. Calculate the solubility in moles per liter in pure water. So that's, again, our molar concentration. Going through our values here, I have my 0.15 plus x. KSP and S are so small, we can drop out the x. So therefore, I've got my KSP, x times 0.15, my molar solubility, quite small. So hopefully you were following along that this was part B of this question here. If I already had 0.15 of this thiocyanate solution present. So we already did this part up at the previous area, and that this was seeing that since SP and S were so small, we can eliminate it, which makes this molar solubility far less than the other one. Come up with any kind of questions you got, and I'll talk to you later. Take care. Bye-bye.